So we can have higher order partial derivatives, second partial derivatives, third partial derivatives, so on and so forth, much like we did back in Calc 1 with functions. So let's take a look at how this kind of I guess you could say a structure might play out. So if I were to start with a function of x and y, basically there's two partial derivatives we could consider. We could take the partial with respect to y, or we could take the partial with respect to x. When we do that, what we end up with is, if on the partial with respect to x side of things, we could have f sub x, or we could write it as partial f partial x. That's what we would get if we took the partial with respect to x, and that is a new function. Okay. Similarly, for partial with respect to y, I could create a new function by taking the partial with respect to y. Now, keep in mind that these partial derivative functions are still functions of x and y. So I can continue this process of taking partial derivatives. So this partial of f with respect to x, I could take, again, another partial with respect to x, or I could take a partial with respect to y. Okay? If I take a partial with respect to x again, what I end up with is I had the partial of f with respect to x, and I did it with respect to x again. Or I have the partial of f with respect to x, and I took the partial with respect to x again. Okay, so this notation, the orders in this notation are slightly different. So if I use the subscript, this would be f sub x x. So the inside in the subscript represents the first partial derivative. The second subscript represents the second partial derivative we took. If I happen to use this notation, the partial notation, I did a partial derivative twice of f, and both times that partial derivative was with respect to x. So I would write it that way. Okay? If I started with the partial of f with respect to x, but then for my second partial derivative I decided to do y, so I would have started with a partial of f with respect to x, but now I'm doing a partial derivative with respect to y. So that's going to give me f subscript x subscript y. The x was the first partial derivative, y was the second. If I use the partial notation, I would have my partial of f with respect to x, but this time I'm doing a partial with respect to y. So I'd still have taken the partial derivative with respect to f twice, but the first time I did it was with respect to x, and that goes on the right-hand side. The second time I took my partial derivative, it was with respect to y. So you'll notice that those orders are different, and you do need to know both orders. So over here, similar process. If I had had the partial of f with respect to y, I could then follow that with a partial with respect to x, or I could follow that with a partial with respect to y. If I were to follow with a partial with respect to x, in the subscript notation, I started with a y, but then I followed that with an x, so I'd have f sub yx. If I used the partial notation, I would have taken the partial derivative with respect to f twice. So partial squared of f. The first time was with respect to y, so that goes on the right-hand side. The second time is with respect to x. So that would be that notation. And then lastly, if I had this partial of f with respect to y and did a second time taking the partial with respect to y, I would have f sub, well, the first time was with respect to y, and the second time was with respect to y. So it would be f sub yy. Or if I'm using the partial notation, I did do the partial derivative of f twice. So partial squared of f. The first time was with respect to y, that goes on the right-hand side. The second time was also with respect to y. So those are the ways we denote that we've taken a partial derivative and the order in which that partial derivative was obtained. So let's go ahead and look at an example. So let's say that we were given f of x and y equal to x cubed y squared plus sine of xy. And we were asked to actually find f sub yx. So this tells me that I must first find the partial with respect to y, and then second find the partial with respect to x of that partial with respect to y. So I need to find the partial of f with respect to y, and then follow that up with a partial with respect to x. So let's go ahead and do that. So the partial of f with respect to y, in my first term, my variable of interest is y, so I treat the x cubed as though it were a constant, and I focus on the y variable. So the partial of y squared with respect to y is 2y, plus, and now I have this sine term, so the partial of sine is still cosine. Leave the argument alone. But then with the chain rule, I need to go inside that argument and also take its partial derivative with respect to y. Now I have x times y. We're treating x as though it were a constant, so I just keep it around. And then multiply by the derivative of y with respect to y. And that's going to give me a 1. So this partial derivative should be 2x cubed y plus x cosine xy. Now, to get what we were asked to find, the partial of f sub yx, I need to take that f sub y that I've already found and find its partial with respect to x. So looking at my first term, the 2 is a constant, the y is a constant, so I'll lump them together. That's my constant. And then if I take the partial derivative of x cubed with respect to x, I get a 3x squared. Plus, now moving to my second term, again I'm looking for partial derivative with respect to x. I notice that I've got x times cosine, and inside that cosine I've got an x. So I'm going to have to use the product rule. So basically we've got what? The derivative of the first times the second. So 1 times cosine of xy. Plus, now I'm taking the derivative, or the partial derivative of cosine xy with respect to x. So partial of cosine is going to give me negative sine of xy. I leave the argument alone. But then I have to multiply by the derivative of the argument with respect to x. So when I go inside the cosine function and I'm interested in the x, I treat y as though it were a constant, and then take the derivative of that x. It's going to give me a 1. So I've got the derivative of the cosine, and then let me put this like that to make it kind of clear. That was the derivative of cosine, and then times the x. So I've got derivative of the x times cosine plus derivative of cosine times the x. Okay, so let's clean this up a little bit. So we've got 2 times 3 is 6 x squared y plus cosine of xy. Looks like that's going to be a minus xy sine of xy. Yeah, I think that does it. So there's our second partial derivative that we were requested to find in the order in which we were told to find it. So let's go ahead and look at a second example here of a second partial derivative. So this time we have our function defined in terms of an integral, which is fine. Keep in mind that sine of t squared, you should recognize that that's not integrable. I can't use u substitution or any other technique that we currently have to integrate that. So looking at the derivative we're requested to find, notice that we are looking at that in this case we'll need to find the partial with respect to x first, and then the partial with respect to y second. That is implicit within that notation. So if I'm doing the first partial of f with respect to x, and this is a function of x and y, using the fundamental theorem of calculus, the y we treat as a constant. So I've basically got an integral from a constant value to x. So we can go ahead and replace t with x, and I get sine of x squared as my partial derivative. And then now, if I do the partial of f with respect to y, I'm doing the partial with respect to y of what I found in the previous partial derivative. And what is that? That's 0. Y is no longer a part of this partial derivative, of this first partial derivative. So this sine of x squared is treated as though it were a constant, and so this would actually end up being a partial derivative. Oops. This should be a squared, and I should have a partial x there. My apologies. There we go. That looks better. And so this would end up being 0.